Well, I may as well begin. So worksheets 16 through 18 are due on the 16th. We're well ahead of my original schedule. I clearly miscalculated, but that'll give us more time to work on the other stuff. It's been a while since I taught this class. Homework number 2 is also due on the 16th. Exam number 2 will be on chapter 16 through 18. It's on the 16th. Please sign in on the sign-in sheet. And yeah. Sorry about the oddness with the schedule. I just miscalculated on some stuff. But that'll give us more time for the geology portion, and I can I've already started going through the slides to make sure we're not going to run out of material. So, talking about chapter 18. Well, we were talking about winds. We talked about the general way winds were formed from atmospheric pressure. Pressure gradient force causes winds to form. They're bent by the Coriolis effect. Now, local winds. So we talked about the large scale winds. Now let's talk about local winds. Local winds are produced from local temperature differences, smaller scale temperature differences. These are small scale winds. These are the sort of winds that are happening around you. These are things like land and sea breezes, which happen whenever you have a land and a body of water, significant body of water. Mountain and valley breezes, which happen when there are mountains and valleys, with valleys. And Chinook and Santa Ana winds, which are specific cases of types of winds that are caused by certain forms of geography and temperature difference. So we'll start by talking about land and sea breezes. When we talk about winds, winds are named by where they come from. So when we say it is a west wind, it is coming from the west. A north wind is coming from the north. A sea breeze is coming from the sea. A land breeze is coming from the land. I mean, unless your sea breeze is coming from the bar, but that's a different sea breeze. So a sea breeze is something that happens during the day. During the day, the land warms up faster than the body of water, the sea, because water is hard to change the temperature of. So the land warms up faster, it gets hot, so hot air rises above the land. You get a low pressure area above the land, and cooler air sinks above the water. So you get a pressure difference from the water towards the land, and you get a breeze blowing from the water towards the land, blowing from the cool towards the warm. And at night, the land cools off faster than the sea does, because again, it's hard to change the temperature of the water. So you get the opposite. At night, you get cool air blowing off from the land to the sea, because it's cooler on land, so you get a lower pressure. It's warmer over the water, you get about a bit higher pressure, and so you get a flow from the land to the sea. Here's sort of a video explaining that process and several other local winds.
Callan Bentley back for another smart figure. This time we're going to take a look at local winds. And after watching this video, you should be able to describe the formation of 4 or 5 different kinds of local wind, explain where they occur and what time of day they occur. So one kind of local wind that you may have experienced is a very pleasant one called a sea breeze. A sea breeze occurs during the day, so the sun is warming up the land. That causes air to rise and ends up taking on a path that looks something like this. You'll notice that this is basically a convection cell, but it's bringing cool air off the surface of the ocean and bringing it over the land. So if you're standing at the beach or something like that, you'll feel this nice cool breeze coming off the water. Very, very pleasant. The opposite of a sea breeze is a land breeze. This occurs at night when the water is the warm one and the land is relatively cool. So warm air rises off of the water and sinks again over the cooler land. And so you end up again getting a convection cell set up, but it's flowing in the opposite direction. So you'll end up having the breeze blowing offshore rather than onshore. One kind of breeze that we get in mountainous regions is called a valley breeze. Valley breezes occur during the day. As air gets warmed up, it rises up the sides of the mountains. As it does that, it brings its moisture content with it, and that will often trigger condensation and cloud formation up on tops of the mountain peaks. If air is rising, elsewhere air is sinking to replace it, and so you end up getting some cool air sinking into the valley. The opposite of a valley breeze is a mountain breeze. This one occurs at night. Cold air sinks and basically rides down the mountain slopes into the valley. At night, the air above the mountain slopes cools rapidly and drains into the warm valley below, and that creates a mountain breeze. One other kind of breeze that's worth knowing about is the Chinook. The Chinook is a kind of wind that occurs in mountainous regions when you end up having an air mass that moves downslope. And as it moves downslope, the air mass expands in volume, and basically it gets warmed up adiabatically. Because it warms up adiabatically, I've shown it very dramatically here with these angry red colors, but it can warm up by a few degrees, and if that few degrees is enough to cross the threshold between freezing and not freezing, it can encourage the melting of a lot of snow in these regions. So Chinooks are very famous as melters of snow. One Chinook-like wind is the Santa Ana winds that occur in Southern California. Basically, if you have a high pressure system that's centered over the desert regions, it can push out some of that hot, arid desert air, which then flows over towards the coast. And that can be a real problem because it can fan wildfires. So we've got these fires that are burning in several locations here, each of them generating lots of smoke, which shows us where the fires are. But basically these are being fanned by these winds that are coming off the desert interior here and then going out over the sea. So those are the Santa Ana winds. Thanks very much for your attention. This has been another Smart Figure.
So yeah, Santa Ana winds are a real problem in Southern California. That's, again, all the wildfires. So valley and mountain breezes are effects in valleys. So during the day, the air above the mountain slopes gets heated and rises up. Cool air will sink down into the valley. Warmer air will rise up the sides of the mountains. You can get cloud formation, condensation and cloud formation. And at night, the air above the mountain slopes will cool rapidly and it will drain down into the valley below, creating a mountain breeze. And the warm air will rise up. And then Chinooks are, again, mountain air moving down a mountain, warming adiabatically, and that can lead to melting of snow. And then Santa Ana is a particular one in Southern California that fans a lot of wildfires. When we measure wind, we have two basic measurements for wind: direction and speed. So in general, if you're measuring, if you have a setup to measure the wind, you have two things. You have something that measures the direction of the wind and something that measures the speed of the wind. Direction wise, winds are labeled from where they originate, where they come from. So a north wind blows from the north to the south. A south wind blows from the south to the north. This is just tradition, but it also, it tells you where the air is coming from. So it gives you some indication of, north winds blow cold, south winds blow warm, that kind of thing. And to measure the direction, we have a wind vane. It's just, you've probably seen one. It looks sort of like it's a solid arrow. It points in the direction the wind is blowing because it has a fin on the back that gets moved by the wind. It points in the direction of the wind. And the direction is indicated either by compass points, north, northeast, etc., or by a scale, an angle from 0 to 360 degrees. And that starts at north being 0 degrees, and then it proceeds clockwise towards east. South, east is 90, south is 180, and west is 270. And prevailing wind, the prevailing wind from in a location is just the most common direction the wind comes from. That's the prevailing wind. So here, for example, winter in the northeastern United States, the prevailing wind is from the northwest. As you can see, much more common that you have wind from the northwest. These are wind roses showing the amount of wind you're getting from each direction. And then here in the northeastern Australia, the southeast trade winds massively dominate, and the prevailing wind is from the southeast. And you can see here the southeast trade winds are much more reliable than the westerlies in the US for persistence of wind. There's more variation here than here. So a wind rose is something that you use to display the patterns of the wind. Here we have a setup for measuring wind. There's a wind vane. Basically, as the wind blows on it, the flat part gets pushed when the wind hits it. This ends up pointing in the direction the wind is coming from. And then there's the cup anemometer up here that measures the speed of the wind. This is a setup of cups. No matter which direction the wind is coming from, this will always spin. And so it'll measure the speed of the wind independent of the direction. So changes in wind direction can be associated with the locations of cyclones and anticyclones. If you've got a cyclone or an anticyclone, a big low pressure area or a big high pressure area, that can cause wind to be flowing away from or towards those areas, which can change the wind direction. And also it gets bent by the Coriolis effect. This often brings changes in temperature and moisture conditions. We live in the middle of a giant flat plain, basically, with very little between us and northern Canada, and very little between us and the Gulf of Mexico, which means when the wind blows from the north, it gets cold. When the wind blows from the south, it gets warm and wet. So yeah, it can be significant changes in temperature and moisture conditions. And since we're in the middle of a continent, the pattern is not the most stable. Now, there are some interesting patterns in throughout the year. There are associations between wind and ocean currents. So El Nino, La Nina, and the Southern Oscillation are all related to each other. El Nino is a countercurrent in the Pacific that flows southward along the coasts of Ecuador and Peru. This has warmer than normal ocean temperatures. It usually appears around the Christmas season, which is why it's called El Nino, because it's a reference to, it's called the boy, but I mean, that's because of the fact that it shows up around Christmas. And it blocks the upwelling of colder, nutrient-filled water, and things like anchovies starve from lack of food. So it affects the fishing, and this causes heavy rains and storms in Ecuador, Peru, Southern California, and it makes it warmer in Central North America. So this pattern. So this El Nino is actually the abnormal state. That's not the normal state. The normal state is La Nina. Sort of. It sort of alternates between them. La Nina is the opposite of El Nino. It's triggered by colder than average surface temperatures in the eastern Pacific in winter. It blows colder than normal air over the Pacific Northwest and the northern Great Plains, while warming much of the rest of the United States. And greater precipitation is expected in the Northwest and colder on the northern plains. So basically, if there are weak trade winds, you get a strong countercurrent, and that's El Nino. So there's a flow of current from west to east. And it makes it wetter than normal in Ecuador and Peru, and pressure decrease in North America. And if the opposite happens, if you have a strong equatorial current and strong trade winds, you get lower pressure over in Australia and Asia, higher pressure over Ecuador and Peru. It's colder, and that's this pattern. And El Nino and La Nina are part of a global atmospheric circulation pattern that affects weather over this huge range, greater than even, it goes across the Pacific, so it's big there, but it also has effects, sort of knock-on effects at great distances from the equatorial Pacific. So the southern oscillation is the pressure change between the eastern and western Pacific. This is associated with time periods between El Nino and La Nina years. There are changes in trade winds. This causes a major change in the equatorial current system, with warm water flowing eastward, things being very unbalanced. So if you have El Nino from December to February, the western side of the Pacific, so Australia, Eastern Asia, Southeast Asia, that area is warm and part of it is quite warm and dry, while the Americas tend to be wet, much wetter. So we're warm and wet and cool and wet. And then in June to August under El Nino, this is all and this is warmer over here and more wet. And it's sort of reversed in La Nina. December to February, Southeast Asia, Australia, that region is all very wet. While the Americas are dry, warm and dry and cool and dry respectively. And then in June to August, it's cool and wet, warm and wet. While this is cool and maybe cool and wet here. This is a relatively complex pattern. So that's El Nino and La Nina, some of the ways things change due to them. Okay, I guess I don't have a smart figure for that. Now let's talk about the global distribution of precipitation. This is a relatively complex pattern because there's a number of things that can affect where you get precipitation. It's related to global pressure and water patterns, where you have high pressure regions, you have subsiding air and divergent winds, and thus dry conditions. So places like the Sahara and the Kalahari Desert are part of the global high pressure zones. They don't get much rain at all because you're getting all the air from the high altitudes, and that's very dry. Low pressure regions have ascending air, converging winds, and ample precipitation. So things like the Amazon and the Congo Basin are both low pressure regions. They have lots of precipitation. They're very wet. But the distribution of precipitation is highly related to the distribution of land and water, because the water to form the precipitation has to come from somewhere, the water, and land has a big effect on temperature distribution, but also if you have very tall pieces of land, it can cause rain to fall out. So large land masses in the middle latitudes often have less precipitation towards the center. So if you're moving, as you move inwards in a large landmass, you get less precipitation because you're far away from the water sources. And mountain barriers have a significant effect on precipitation. Basically, if you have a body of water and you're blowing all your air with lots of water vapor in it, and it hits a mountain, it gets pushed up. And that cools the air down, and all the water falls out. So you get, on the side where the wind comes from, you get very wet conditions. And on the side, the leeward side, so the windward slope receive abundant rainfall from orthographic lifting, because as the air travels up the mountain, all the water condenses out. And then the leeward slope, downwind from the mountain, is very dry, because all the water was squeezed out on the other by the mountain. So it's usually deficient. And there's what's called a rain shadow desert. So here are some examples. Distribution of precipitation. You can see there's lots of rain here at this low pressure near the equator. There's a dry strip here at the high pressure zone. And then there's more rain a little further north. Here you can see these dry areas where there are mountains. So you have mountains, and then the wind here is coming from the west, hits these mountains, and you have a desert after it. Similar things. If you see the interiors of continents, like up here, is dry. And there's some similar deserts on the windward side of the southeast trade winds. I think there's some mountains along here, but also the interior of the continent. So that was the end of chapter 18. Do you have any questions? Anything you'd like me to go back over? Because we have plenty of time. Okay, well then, if there aren't any questions, I'm going to move on to chapter 2. So, first section was on astronomy. The most recent one was meteorology. Now we're going to move on to geology, our first geology section. So let's talk about matter and minerals. So the world we live in is made of stuff. That is not a very deep statement. So we're going to talk about the various properties that an earth material has to possess to be considered a mineral and go over what each characteristic is. We'll look at the structure of atoms. We'll compare and contrast the 3 primary particles contained in atoms. We'll distinguish among types of bonds: ionic bonds, covalent bonds, and metallic bonds. Those are the 3 common types of chemical bonds. We'll look at the properties used in mineral identification. We'll go over what makes something a mineral, and then we'll go over how you figure out what mineral you're looking at. We'll look at the common silicate and non-silicate minerals. We'll describe what characterizes each group. And we'll talk about Earth's mineral resources in terms of renewability and differentiate between a mineral resource and an ore deposit. And the difference is actually pretty simple. If you'd like another resource, just finished on Crunchyroll was the anime Ruri Rocks, which is all about mineralogy and geology. It is the main character is originally inspired to find pretty rocks, and it sort of goes on from there. It has some excellent descriptions of how stuff moves throughout the earth, how minerals, how you find and identify things, how you can find various minerals, how various minerals are produced and formed. Most of the geology is excellent. The only thing that I find unrealistic is that the main character is far too lucky in finding minerals, and all the deposits he finds are way too big. But otherwise, it's just exaggerated a bit. There's a scene where they find literally pools of opals. It's kind of ridiculous. So let's go into and it is focused on more targeting things like gemstones, pretty rocks. Because it starts with this character he finds that buying crystals is very expensive, and that her grandfather used to find crystals, and then she runs into a geologist grad student. You can identify it from the large hammer. So let's talk about what a mineral is. A mineral is something on Earth that makes up stuff that is naturally formed. So cubic zirconium you got from a lab, not a mineral. So if you make it artificially, it's not a mineral. But naturally occurring, it's inorganic. That means it doesn't come from a living thing. So amber, not a mineral technically. It's solid. So, liquid mercury, not a mineral, or just water is not a mineral. And it possesses an orderly internal structure of atoms. This means it's not only solid, it has a distinct, clear crystal structure. This means glass-like things that are glasses, like obsidian, are technically not minerals because they don't have an orderly crystal structure. And it has a definite chemical composition. If we're going to define a mineral, we're going to be defining something with a definite chemical composition. Now that you can have multiple minerals with the same composition, but any mineral has a consistent up to impurities chemical composition. Now a rock is any naturally occurring solid mass of mineral or mineral-like matter. So basically, there are some things that don't quite technically qualify as minerals, but they make up parts of rocks that we'd like to call rocks. So we actually classify them as, I believe, mineraloids. So these are things like coal, which coal is basically a rock. If you've seen a lump of coal, it's a rock. But coal is not a mineral because it's got an organic origin. So it's a mineraloid. And then obsidian. Obsidian is naturally occurring volcanic glass that cooled too fast to have a regular crystal structure, so it's not technically a mineral, but it's like a mineraloid and you'd still consider it a rock. But they have to be natural. So rocks are naturally occurring solid mass of mineral or mineral-like matter. Because there's a few things out there that don't technically qualify as minerals, but we really would like to put them in the same category. We'd like to say that if they show up in a rock, it's still a rock. So most rocks are aggregates of minerals. So here is a chunk of granite. It's a rock. Each of these little different colored areas are individual crystals of minerals or individual minerals. So this is quartz. This is hornblende, the dark areas, the pink areas, the pinkish areas are feldspars. Those are the individual minerals that make up the rock. Some rocks are made of only one mineral. Some rocks are mixtures. So limestone is made up almost pretty much entirely of calcite. So one mineral, all the same mineral. But granite is a bunch of different stuff. And then you could have something like quartzite, which is made of quartz. So here is a short video about the difference between minerals and rocks.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the difference between a mineral and a rock. Let's start our discussion with a picture of a cookie. You can, when you look at a cookie, distinguish between the ingredients and the cookie as a whole. For instance, here are two chocolate chips, and chocolate chips are ingredients in that cookie. Those chocolate chips are compositionally and texturally distinct from the background material of the cookie. In the same way, minerals are related to rocks. So here, for example, is a rock. This is a rock called a granite. And you can see that there's different colored patches in that granite. So for instance, We see a sort of pink patch right there. There's a black patch right in there. There's a white patch over here. There's a little gray patch over on this side. That sort of thing. Each of those different colored patches is a mineral crystal. So here we see a quartz crystal, a hornblende crystal, and a feldspar crystal. All right? Everything you see down here on the bottom is a mineral, and those minerals are basically the ingredients that make up the rock, known as a granite. Rocks are made of minerals. Those minerals are there even if you can't see them. So here's a comparison between two different kinds of rock that we'll learn about in the next chapter, igneous rocks. And you can see that the crystal size is really different between the granite on the left and the basalt on the right. Even though you can't see the crystals in the basalt with the naked eye, if you examine the rock with the microscope, you can see that the mineral crystals are in fact there. Of course, that's not really sufficient to define a mineral. Minerals, they have to meet 5 criteria. They have to be solid, they have to be naturally occurring. Generally, they're inorganic, which means that you don't need living organisms in order to make those minerals. Living organisms in some cases can make mineral deposits, like shell material in a lot of marine organisms, but you don't need that critter in order to make that mineral crystal. Minerals have a characteristic chemical composition, which means we know what elements that they're made out of, and they have an orderly crystalline structure, which means if you zoom in to the atomic level, you'll find that the atoms of that mineral are orderly arranged relative to their neighbors. If you were to zoom in instead and find disorder on the atomic scale, then that would not be a mineral crystal. That'd be something like glass. And the glass that makes up this beer bottle here is not a mineral because it's disordered on the atomic scale. What about the water in that glass? Let's imagine that we froze that bottle and that water transformed to ice. Would that ice be a mineral? Well, it's solid, it's naturally occurring, it's got a characteristic chemical composition, hydrogen and oxygen, it's got an orderly crystalline arrangement, and it is inorganic. So it meets all 5 criteria, and therefore ice qualifies as a mineral. Thank you for your attention. This has been another Smart Figure.
So that's how you can tell the difference between a mineral and a rock. Rocks are made of minerals. So the building blocks of matter are atoms. And all minerals are built from atoms. Atoms are more or less the smallest particles of matter. They have parts, of course, but stuff is built from atoms. They contain a central nucleus that is made of protons and neutrons. Protons have a positive charge, neutrons are neutral. They're both dense, massive particles. They're both made of up and down neutrinos, more or less. Particle physics gets weird, but they're both primarily made of up and down neutrinos with a different number each. One of them is 2 ups and a down, and the other one is 2 downs and an up, and I can't remember off the top of my head which is which. But they're similar particles that live in the nucleus. One has a positive charge, one has neutral charge. And then surrounding the nucleus, there are electrons. The electrons are much less massive than the protons and neutrons. They're about a 2,000th of the mass. They effectively have negligible mass, and they have negative charge. And they take up the outer, they're surrounding the outside of the atom, and all of chemistry involves interactions between the electrons. The protons and the neutrons just stay in the nucleus and have a charge. Protons and neutrons don't do stuff unless radioactivity or nuclear reactions start getting involved. And that generally doesn't happen very often. Well, radioactive decay happens, but generally pretty slow. So here are a couple models of an atom. This is a neither of them is exactly right. This is sort of a classic drawing. You have the nucleus, made of protons and neutrons held together by the strong nuclear force. And then you have electrons orbiting around it. This isn't an accurate thing because these orbits are not nice, perfect circles. This cloud that the electrons are in is a more accurate model. So these clouds are not all spheres, just, well, how many electrons are here? 1, 2, 3, 4. It's 1, 2, 4, 6, 6. Yeah, this wouldn't be totally accurate, but some of the electron clouds are spherical. So it's roughly spherical, and then the nucleus in the center. There's a few issues. The nucleus is really dinky. It's not anywhere near that big. It's a lot smaller. But yeah, this is sort of the idea. There's a nucleus with protons and neutrons in the center, and then there are electrons that are attracted towards that nucleus because they have the opposite charge and surround it in something closer to an electron cloud. Their location is fuzzy. To define an element, so I don't feel like actually taking I could do this one. So, there's a whole bunch of elements. Here's the periodic table of the elements. To define an element on the periodic table, you'll notice that each box has a few numbers in it. Has more numbers than we're going to talk about. But everyone has a number up in the upper corner. Like for carbon here, it's 6. That is the atomic number. It's the number of protons in the nucleus. And that is what defines what element you're dealing with. So anything with 6 protons is carbon. Anything with 8 protons is oxygen. Anything with 26 is iron. So that determines the chemical nature because it determines how many electrons will be attracted to it, because it would, it determines the charge of the nucleus, and how many electrons are going to be naturally around the outside of an atom helps figure out what its chemistry is going to be. And an element is all atoms with the same number of protons. They have the same chemical and more or less the same physical properties. Because their mass changes, you can have the mass change. You can have more or less neutrons. So the mass of that particular thing can change as an isotope. And for little elements like hydrogen, that can have somewhat different physical properties. Just because for hydrogen, the most common isotope is deuterium, that doubles the mass. That has a significant effect. But for like, I don't know, uranium, going from 238 to 235 is not a big change. I mean, it's a significant change because 235 does fission and 238 does not. So if you want to make it a boom, the 235 is what you need, but that's something different. But this is a tool scientists use to organize the known elements. The periodic table is the tool. And there are 90-ish naturally occurring elements. Naturally occurring, we get elements up to uranium, which is 92. But there's a couple up here that don't occur naturally. You do actually get a little bit of naturally occurring plutonium. So I think that might be 91. But there are a couple, I don't remember which ones exactly, that don't occur naturally. But basically, well, actually, I can tell the synthetic ones are the outline ones. So, technetium doesn't occur naturally. I thought there was another one. And promethium. So technetium and promethium don't occur naturally. You do get a little bit of naturally occurring plutonium, but it doesn't last. So basically, in certain places geologically, you can have uranium deposits basically generating plutonium because they're acting as nuclear reactors and generating plutonium, much the way we generate plutonium ourselves. So you can get a tiny bit of natural plutonium, but it's negligible. All significant quantities of plutonium we have are synthesized. But it is possible to basically have radioactive decay. If you have certain radioactive decay products, slam into uranium and can turn it into plutonium. So this is a periodic table of the elements. The top number is the atomic number. Then there's the symbol, which is just based off the name, though a bunch of them are based off of names in other languages, in either Latin or German. A bunch of them are German. So if it doesn't look like anything like the English name, it's probably Latin or German. So like gold is AU, that's from Latin. And then where's another one? Tin, I think the SN is from the German, if I remember right. But I could be wrong, it might actually be Latin. But a few of them are from other names. Because they're based off historic names. Like potassium. Potassium is a funny one. For example. The older they are, the more likely they're not going to match up with English. And then there'll also be an atomic mass. The atomic mass that you're seeing here is an average of all the naturally occurring isotopes. For any particular isotope, its atomic mass is going to be the number of protons plus the number of neutrons. But like, if you have something like hydrogen, you'll see the hydrogen up here is 1.00794. That's because there's a decent amount of naturally occurring deuterium out there. So hydrogen that has a mass of 2. So 1% or so. So it kicks it up a little bit. And that's why there's some funny ones out there like fluorine is like 35.453. That's because there's about 25% of fluorine. It's another isotope that's at 37 instead of 35. So bonds. And what's called the octet rule. Atoms would like to have a total of 8 electrons in their outermost shell. Technically, this should vary as you get to bigger and smaller atoms. The only thing you'll normally run into is hydrogen, which wants to have 2. But in general, they want to have 8. It turns out, because of the sizes of shells, the outermost shell that always does the interacting basically always has 8. There's some funky stuff that has to do with the order things get filled. But it really wants to have 8. So the octet rule is good and solid. And a chemical bond is a transfer of sharing of electrons to achieve a full valence shell. So there's basically 2 things you can do. If you have like one electron in your outermost shell, you could get rid of that electron and be down to have a full 8 shell beneath. And if you had a friend who was just missing 1 electron, they could grab that electron and they could be happy. So if you were sodium at 11, would like to lose 1 electron and have a full shell, and you have the friend chlorine at 17 who'd really like to gain an electron and have a full shell, then you could give your electron from sodium to chlorine. Sodium will get a full shell up here. Chlorine will get a full shell here with 2,8 and 288. And they will both be happy, but the sodium will have lost an electron, so it will be positively charged. The chlorine will gain an electron, so it will be negatively charged. They will be attracted to each other. And this will form an ionic bond, and a mineral we know as salt, halide. So table salt is sodium and chlorine. You wouldn't like to encounter sodium and chlorine on their own. They're both quite nasty. Sodium ignites on contact with water, and chlorine is gloriously toxic. But table salt's great. So a chemical bond is something that can form if you share, transfer electrons. But it might be that you're more towards the middle, and it would be easier if you could, instead of having to give up or lose an electron, which isn't the greatest, because you'd still like to be neutral. You wouldn't like to gain or lost an electron. You could just share with your neighbor. So if you had two hydrogens and an oxygen, the oxygen is short by a couple of electrons from being full, and the hydrogens are each short by an electron each from being full. So if the oxygen shares an electron with one of the hydrogens and shares an electron with the other hydrogen, everybody's full and happy, and you have water. And that is a covalent bond. So if an ion has lost or gained an electron, if an atom has lost or gained an electron, it becomes an ion. That is a positively or negatively charged atom. These are strongly attracted to each other because they have a positive or negative charge. And so ionic bonding is when one atom gives up one or more valence electrons, the other atom accepts them, and this forms ionic compounds. The classic example is sodium chloride, table salt, but there's a ton of these. And a lot of minerals are ionic. So this is sodium chloride. So sodium has 11 electrons. It would like to be at 10. Chlorine has 17 electrons. It would like to be at 18. So the sodium loses an electron. The chlorine gains it. The sodium is happily at 10 electrons, but now it's positively charged. It's an Na plus ion. We put the charge up and to the right of the name of the atom. So Na plus, and the chlorine is Cl minus. If it had lost 2 electrons, that'd be 2 plus. Or plus 2, I don't remember the exact notation. I think it's plus 2. And then they're attracted to each other, so they form this nice crystal structure of table salt. Now, covalent bonding doesn't have any ions. Nobody is losing electrons. Turns out if you bring two atoms close together, they can share their electrons, and this is actually much stronger than ionic bond. So the formation of a covalent bond, you have 2 hydrogen atoms. Each of them is short an electron. They would like to share those electrons. They come together. Then they have 2 electrons forming a single big cloud around both of them, and this pulls them together. They combine to form a hydrogen molecule. The bonding changes the shape of the electron clouds. And then metallic bonding also contains ions. We have packed metal ions where in metals, basically, they have very loosely bound valence electrons. And so what you can have is you can have a whole bunch of them stuck together, and the valence electrons just sort of float freely around. This is what makes them good at conducting electricity, because they're freely floating around electrons, but it also makes them good at transmitting heat and other things. So packed and makes them shiny. They reflect light well because of this as well. The packed metal atoms have valence electrons that are free to move throughout the structure. So if you pack all these together, all the metal are sort of ions with sort of electrons, all the extra electrons sort of flowing in between. There's a sea of negatively charged outer electrons. And that's metallic bond. And when we look at identifying minerals, we can look at the various properties of minerals. And one of these is literally looking at the optical properties of the mineral. So luster is a measure of how it looks in reflected light. That's like, is it shiny? Is it dull? What does it look? How does it reflect light? Color is actually one of the weakest identifiers for minerals, because it turns out for a lot of minerals, the color can change dramatically just by the addition of a small amount of impurity. So rubies and sapphires that are red and blue respectively are both corundum, the same mineral. Rubies have a tiny bit of chromium in them that makes them red. Blue sapphires have, I don't remember, it's like magnesium or copper. Sapphires more generally used, but there are other. And then if you've ever used an emery board, emery is also corundum, but with iron or magnesium in it, I think iron, and it's black. And also doesn't tend to form very big crystals, so it's used as an abrasive in an emery board. A much better identifier is what's called streak. This is the color of the mineral in a powdered form. And the way you get this is you take it and you take the mineral or whatever you're trying to identify, and you make a streak on a rough surface. So today, modern day, they use these ceramic streak plates. Traditionally, if you wanted to identify precious metals this way, you use something called a touchstone. You may have heard of a touchstone. A touchstone is a stone that you take your thing you think is gold and you rub on the touchstone, and you make sure that the streak it leaves is the right color for it to actually be gold and not something else. And then the ability to transmit light. So light can travel through a mineral, causing it to be translucent or transparent. That's a significant indicator. There's some other optical properties. Some minerals have things like bipharingens, where they will like split light and do other funky things. So here are some examples of lusters. This is a metallic luster. This is pyrite over here. And this is limonite, non-metallic luster. They're both yellow. Pyrite is very golden color. It is not gold. That is what's known as fool's gold. This is iron sulfide. And is actually fairly common. And I know there's a decent amount of pyrite over in Galena because of the lead mines. Because the lead ore they're pulling up, Galena, named after the ore, is also a sulfur compound. So it's lead sulfide, and this is iron sulfide. Now, these are all quartz. These are citrine, amethyst, and just plain quartz. Now, they're all different colors, but they're all quartz. And in fact, there are even more colors for quartz. You can get, there's like rose quartz, which is reddish. There's blue and green quartzes out there. You can get quartzes in just about every color. And you can get quartzes where the colors vary through the crystals even, which is rare, but incredibly cool when it happens. Now here, these are both hematite. They're the same mineral, but various impurities are making them have different colors. So one is much darker than the other. But you can see how they have the same streak. And if you did pyrite on these plates, so if you did gold on one of these plates, you get a gold streak. Gold looks like gold. But if you did pyrite, which also looks like gold, and did a streak of it, you would find that it put out a black rock. So the color can be quite different. So here's a short video about identifying minerals with things like color and other properties.
Hi, this is Callan Bentley. Welcome back for another Smart Figure. After watching this video, you should be able to describe the pros and cons of using mineral color as a guide to identifying minerals. When you look at a specimen like this, what's the first thing that catches your eye? Is it the shape of the crystals? Is it the number of crystals, their different orientations? Or is it the color? If you're like most people, color is one of the first things that you notice about a mineral or a rock. If we look at this granite, for instance, it's the different colors of the minerals that allow them to stand out to our eyes and allow us to identify quartz or hornblende or potassium feldspar. But color is not all that reliable an indicator of which mineral you're looking at. For example, here are 4 different colored specimens, but they're all the same mineral, quartz. Here are 5 different colored specimens, but they're all the same mineral, fluorite. What makes these quartz samples and fluorite samples different colors? It's just little impurities, small amounts of other elements that get into that mineral and stain it a different color. You could think of this as like the food coloring effect. If you're making a batch of pancakes and you put in a few drops of green food coloring, suddenly it looks like you've made something very different indeed, but it still tastes like pancake. More reliable than color is luster. Here's an example of that. This is the mineral galena. You can see a tarnished example of galena on the left, and you can see a relatively fresh specimen of galena on the right. Galena has a metallic luster, meaning that it reflects light like a metal. So that's more reliable than color as an indicator of which mineral you're looking at. Then there's also streak. Here's an example of the mineral pyrite, which you can see has a nice golden color and a metallic luster. When you scrape pyrite against a streak plate, you'll see that it leaves behind a characteristic dark gray colored streak. And the color of that powdered form of the mineral is actually a more reliable indicator of which mineral you have than the color of the mineral itself. Thank you for your attention. This has been another Smart Figure.
Basically, the streak, by turning it into a powder, it kind of obscures the impurities. Now, another more useful way to identify minerals is the shape of the crystals. Because every mineral has a unique crystal structure, it turns out that affects the shape of crystals it forms. So you can have fibrous crystals, bladed crystals, banded growth, cubic crystals. So the shape that crystals grow in, like when we saw in the video, those fluorine examples, they were all those neat little octahedrons. That's a good way to identify fluorite, because fluorite is one of it has several different ways the crystals can grow, but one of the common ones is those octahedrons, and it isn't that common of a crystal structure elsewise. Oh wait, we were talking about other identification. I was gonna add another video and I missed it out. I'll play this one first, but I can pull up that video after this.
Deep beneath the earth in Chihuahua, Mexico, grows a real-world fortress of solitude.
So here's some of the most impressive crystal finds.
In 1910, in the Nica mine in Mexico, the Penoles Mining Company discovered what came to be known as the Cave of Swords. It was an 80-meter-long hallway with beautiful gypsum crystals growing up to 2 meters in length. Unfortunately, the cave was opened up for exploration and later tourism, which destroyed many of the crystals. 90 years later, 2 miners working for the same company stumbled on another cave, except this one was much, much bigger. Nica sits on an ancient fault line above a magma chamber. This heated the groundwater and filled it with sulfide ions. So when this hot sulfide brew met with the cool oxygenated water in the cave, they didn't mix exactly, they kind of sat on top of each other. But the oxygen began to diffuse into this rich sulfide soup, and slowly, at an infinitesimal pace, these crystals began to form. They have been growing for 500,000 years. Today, the largest crystal in the cave is 12 meters in length, 4 meters in diameter, and 55 tons. It is 20 times bigger than any previously known crystal. Amazingly, there's no limit to how big these crystals can get. Given enough time, they will grow ever larger. These are Fortress of Solitude crystals. They are Superman crystals. One big difference between the Fortress of Solitude and the Cave of Crystals is the temperature. The Cave of Crystals is blisteringly hot. It is 50 degrees Celsius or 122 Fahrenheit, and the humidity level is a constant 90%. Even wearing special cooling suits filled with ice and water, researchers were only able to spend about 40 minutes down there. These crystals grew underwater. It's only in the last 20 years this mining company has pumped out all of the groundwater so they can extract various precious ores from the area. But as soon as it doesn't make economic sense for this mining company, the crystals will be resubmerged, returned to their underwater existence. And this is probably for the best, because while it's incredible we get the chance to study them now, that's their natural environment. It's where they grew, it's where they can keep growing. And I think considering how beautiful but also how fragile these are, just knowing that they're under your feet growing ever larger is more than enough. Subscribe here and watch more videos here. This isn't gypsum, this is salt. The NICA project is doing a ton of amazing science around this, including looking at ancient life forms in these crystals and trying to find their closest relative. I've included a link down below if you're interested in learning more about that.
And that cave has actually been reflooded since that video was made. So let's go through these properties and then I'll have another one if it doesn't get mentioned. So mineral strength is how easily minerals break or deform. This is determined by the bonds. So these are things like a measure of hardness, the ability to resist scratching or abrasion, cleavage, the tendency to break along planes of weak bonding, fracture, the random pattern of breakage. So if something breaks and it forms a nice flat surface, that's cleavage. If it breaks and it's sort of random or it's a smooth, so if it forms like a sort of clamshelly arc, that's fracture. Tenacity, which is the resistance to cutting, bending, or deformation. These are ways you can identify properties of the mineral. And then specific gravity is a matter of mineral density. Okay, and I think, yeah, this was
Hi.
hardness and cleavage I have coming up. But yeah, I want to show you one more thing about how minerals react to light that I forgot to add. But I have it in another PowerPoint, so I'll just quickly open it up. Enable. This is a video about another way of resin.
Hello, my name is Deborah Wilson. I'm the collection manager for the section of minerals here at Carnegie Museum of Natural History. Today I'm going to show you an interesting highlight opal. Most highlight is very fluorescent, which means under ultraviolet light it'll glow. I've actually pulled a couple of samples of fluorite, and fluorite was the first mineral species that fluorescence was discovered in, so it was named after the fluorite. Certain specimens will have what we call activator elements in them that when the ultraviolet light is shining on it, it kind of excites the electrons and they move up to a higher state, and as they're moving back down, you'll see the light in your visible spectrum. Here are two specimens of fluorite from England. You'll notice that they are different colors in natural light, but you'll see when we put them under the ultraviolet light that they fluoresce almost the same identical color. This is a VUG as what we call kind of an opening in the rock where these minerals are growing, there's little quartz crystals and chalcedony, which is a variety of quartz, that have a coating of hyalite opal on them. And this is from the Candelaria mine in Sonora, Mexico. So let's take a look and see what this hyalite opal looks like under the UV. This is shortwave ultraviolet, which most species that fluoresce do the best under shortwave. Some things will also fluoresce under long wave. Some will do either one or the other. Hyalite normally does shortwave, but we'll take you up to Hillman Hall and show you hyalite opal that actually fluoresces under long wave. So if I have a little ultraviolet pen, it'll penetrate the plexiglass and will actually make this fluoresce. Now this one also is so highly fluorescent, it will start glowing under natural sunlight. This deposit of hyalite opal was discovered in Zacatecas, Mexico in 2013, and it's all been mined out. There's no more coming out. This piece of rough is got little globular growths, it looks like, that you'll be able to see better when I make it fluoresce. And this gemstone is the second largest stone that was cut from everything that was recovered there. So let me show you how it fluoresces. It turns this bright green. You can see it a lot better on the matrix, and even the gemstone just pops when you hit it with the UV light.
If you like this video, please press like and subscribe. And also, please visit us here at the Carnegie.
So another property that's useful is specific gravity. And we talked about various things. Color can be useful more for figuring out like things about the history of a mineral, because those impurities tell you about exactly what was going on. So hardness. Hardness is a measure of how hard it is to scratch something. And for mineral identification, the primary tool used is the Mohs scale, which is a relative scale. Because the Mohs scale measures how easy it is to scratch things compared to other common minerals. It goes from 1 for the softest mineral to 10 for the hardest. Softest mineral out there is talc. Hardest mineral out there is diamond. But here you can see what that looks like in an actual absolute hardness scale. The difference between the low end, they're all very close to each other. And it gets way huge changes at the high end. Because, between corundum and diamond, there's a huge change in hardness. But it's only one step on the Mohs scale because there's not much in between them. And then the way you test hardness is you try and scratch it with various things or see what it scratches. Harder objects will scratch things that are lower on the hardness scale and will be scratched by things higher on the hardness scale. So if you have something that can be scratched by a screech plate but will scratch glass or a knife blade, it's probably a 6 because it's in between 6.5 and 5.5. So here's a short video about mineral hardness.
Hi, this is Callan Bentley. Welcome back for another smart figure. After watching this video, you should be able to describe mineral hardness, where it comes from, how to measure it, and why it's useful in identifying minerals. So here's an example of a mineral. We can see that it's sort of transparent and light colored, doesn't appear to have a metallic luster, but how can we identify it? We've got to look at the physical properties of this mineral, and one of the physical properties that's most useful is hardness. It's important to realize that hardness is not mineral strength. It is merely resistance to being scratched. So if you want to figure out a mineral's hardness, you've got to try to scratch it. What should you scratch it with? whatever's handy. There are certain tools that are common everyday objects that have a known hardness that are useful in assessing mineral hardness. One of them is a penny. So what you do is you simply take your penny, you try and scratch the mineral with it, and once you've done that, if you succeeded in scratching the mineral, as we did here, leaving behind little gouges in the mineral face, then that means that the penny has got to be harder than the mineral. So the mineral is therefore softer than the penny. This is the basic idea behind the Mohs scale of hardness. This is a relative hardness scale developed by a mineralogist named Friedrich Mohs, and it ranges from the softest known mineral, talc, all the way up to the hardest known mineral, diamond. There's 8 steps in between those two. Our penny is an example of an object of known hardness. So a penny is a hardness of 3.5. The previous example where we were able to scratch the mineral with our penny means that our mineral must be softer than 3.5. Another object that's often useful is your fingernail. Your fingernail is a 2.5 on the Mohs scale of hardness. A wire nail clocks in at 4.5. A knife blade or a piece of glass is 5.5. And the ceramic streak plate that we use for assessing the color of the powdered form of the mineral, that streak plate is a 6.5. So when you're identifying minerals in the laboratory, you basically want to bracket a mineral's hardness between two of these numbers. So for instance, if it is softer than the streak plate but harder than a piece of glass, that means it's somewhere between a 6.5 and a 5.5 on the Mohs scale of hardness. Now the Mohs scale of hardness, like I said, is a relative scale. It's not actually an absolute scale. So the difference in hardness between, say, talc and gypsum is actually much less than the difference between corundum and diamond. Just the same, the Mohs scale of hardness is really useful, especially for introductory geology students. Here are 6 sample minerals that all could look very similar to one another. The fluorite obviously stands out because it's bright purple, but keep in mind that color can really deceive you when it comes to identifying minerals. So rather than relying on color, let's check the hardness of these different minerals. Calcite will clock in at around a 3 on the Mohs scale of hardness. Dolomite will be about a 3.5. Halite is around a 2.5. Gypsum is around a 2. Fluorite is a 4. And quartz is a 7. Let's slide that fluorite over to the side here and consider it in a little more detail. If fluorite has a hardness of 4, what common everyday objects will scratch it, and which ones will be scratched by it? If you answered that the knife, the wire nail, and the streak plate should all be able to scratch it, since fluorite is a 4, and that fluorite will be able to scratch both a copper penny and your fingernail, then that's the answer I was looking for. Good job. It's exactly that kind of logic that you need to use for assessing mineral hardness.
And then cleavage is how it breaks. So these are some examples of cleavage in one direction, like in mica. This side has fracture, but these two sides have cleavage in 2 directions. It's a feldspar. These are 2 directions, but not at 90-degree angles. So fracture, but cleavage over here. You have 3 directions like halite, all at 90, 3 directions not at 90-degree angles, and then 4 is fluorite. But I think we're going to stop there for today. We'll go over this again next time. Yeah, have a nice day, and I'll see you all next week.